Imperial and Sheffield, quantum song. Quantum cascade lasers have also been grown by MOBP, and this is a world first that people used to say it couldn't be done by MOBP, it could only be done by MBE. Because we have equipment and personnel who are very good, they took that as a challenge and they demonstrated that you can do that as well, if not better. So in fact now, groups at Harvard and places like that are now starting to use MOBP as the default way of trying to produce high-quality quantum cascade lasers. So you can see that there are laser emissions in the infrared. In this case, you can see that we can actually have lasing even at above room temperature. At 350 Kelvin, these devices can emit CW at 7 to 8 microns. Quantum dot lasers, again, they've demonstrated that they can get good quantum dot lasing emission from gallium arsenide, something that again they said that could not be done by MOBPE. Having this capability at Sheffield has allowed us to show that there's nothing fundamentally that stops you. Nitrides of course is very important now because all the blue lasers, blue LEDs that are going into your Blu-ray DVDs are produced by this gallium nitride technology. We've decided that that is not something that we want to compete with because that works in our commodity product. You can buy blue lasers, 4 or 5 nanometer lasers. Every time you buy a Blu-ray player, you get one thrown in for free. So what we've said is, look, instead of just sticking with the blue, what is more important and interesting and more challenging is to move to the ultraviolet. So we're starting to look at 315 nanometers. And there are all sorts of tricks you have to do with the buffer layer because there isn't a gallium nitride substrate. So you tend to do the growth on sapphire substrates. So we're starting to get very good output power, electroluminescence in the ultraviolet, and this will have applications for all sorts of biological applications where people want cheap, low power, compact ultraviolet sources. So those are some highlights of the growth. And for device fabrication, let's see the list. This is an oxide aperture VCSEL where you grow the drag stack, put it in the steam oxidation kit, and we can then oxidize the aluminum outside. You can see the tiny aperture in the middle through which the light will be emitted. This is work done by my own group on single photon avalanche photodiodes in collaboration with J.P.R. I said to you earlier on, there was a lot of interest in making a single photon emitter using the quantum dots. Well, at the far end of your system, you have to have a detector that can detect one photon. So the photocurrent that flows is very small, and the way that we amplify that is to use an avalanche photodiode in Geiger mode. So this is the sort of, it's a double diffused guard ring structure. It took my postgraduate students about 8 weeks to make one of these. So it's a very time-consuming process because the slightest thing that is misaligned or goes wrong results in a failure. We've made the world's first DBR, deep Bragg mirror, Bragg rating for QCL. We did that by just etching a periodic grating on the facets of the ridge quantum cascade laser structure that allows you to get very accurate mode control. So instead of having a broad emission from the lasing, you've seen this picture already. And of course, I've been talking a lot on optoelectronic devices, but we can also do transistor-type devices using these 3 files. So in the case of gallium nitride, because of its very large band gap, these devices can operate at incredibly high voltages and high currents and high temperatures. So we have the capability to grow and to process transistors with something like 0.25 micron gate lengths. So it shows the sort of range of things that can be done in Sheffield. So I think this must be the final slide. There are people who are using quantum dot emitters to make swept sources. So for things like optical coherence tomography, where people want to look for things like cancers that are just tumors that are just below the skin. They want an infrared light source, but who they can tune the wavelength and do it in a swept way, so it allows you to get a simple, easy way of getting a swept source there. Now, you can get swept source lasers, but they'll be the size of this table. There, what they've done is they put, it's a complicated structure, they've got quantum dots there, they've got a long cavity and a short cavity there, and by just clever biasing arrangement, they can actually get to sweep the wavelength, and the whole thing is about 1 millimeter long. So, so these are things that we're doing with the group at Cardiff University and Medical Electronics Group. So I think there are lots of new things that you could do in the longer term. As I said, it's 3-5 on silicon, maybe think of ferromagnetic materials, trying to do quantum dots and quantum wires. There's still a lot of scope to extend that. So but these are things that you can only do when you have a team of extremely expert people who are not distracted by things like teaching and student issues, and they can have very good facilities there. And this is not going to happen under normal R&D funding, but it can only be done when we have a facility like the sort of Sheffield Center facility. So I think with that, I'll bring my talk to a close. Thank you very much.
Thank you very much, Mr. John. Now is the open question. Any questions? From other members? Any questions from you? There's no question. Cyberjaya, any question? I have a question. I think this slide skip a slide that you mentioned about the IP issue. I think when the other universities submit their design, I think there's a lot of trust to share the design.
Yes. I mean, I glossed over that in this particular talk, but those are the sort of things. It was not a major problem about 30 years ago when people were doing very basic research. I don't think anybody had really thought that a company was going to be formed or they were going to become very rich on the basis of that. But of course, clearly as time has progressed, that people can see opportunities. And universities want to spin out their own companies, they want to become directors of their own companies. Then if they're sharing, they have to share the ideas with us because we can't produce the material without them telling us what we're trying to do. So there has to be this understanding, and I think the easiest way to do that is to make sure that you have very clear non-disclosure agreements, and of course who is contributing what to the idea to make it work.
So now it's a standard practice that they have to sign a
non-disclosure. No, they don't have to unless they bring it up themselves. But if they do that, see, most of the work is still done on a research basis, and it's because we have the same team of most of the people who are here have been here for many years. Some have been there since the beginning. So the academic community knows these people and trusts them, that they're not going to steal their ideas and rush off and sell it to someone or form their own company.